Welcome back to Physics 192. I'm Gerard Blanchard. Last time I introduced you to the strong nuclear force which allows protons to combine together to form nuclei of different elements. So one element can turn into another element by adding or taking away protons, and the strong nuclear force also allows protons to attract neutrons into the nucleus to give you different isotopes of different elements. This time, I'm going to introduce you to the weak nuclear force, which does something a little different. The weak nuclear force, or more precisely, the weak nuclear interaction, permits three different reactions to happen. You'll see that all three of these reactions are related to one another. The first of them is that a neutron can change into a proton plus an electron and an anti-electron neutrino, as you can see in this reaction. A neutron goes into a proton plus an electron, the E- is an electron, plus an anti-neutrino. That is the nu, that's a Greek letter nu, with a bar on top of it. The bar signifies an anti-neutrino. Now, this reaction balances both the nucleon number. A neutron is a nucleon, and a proton is a nucleon, so we have one nucleon on either side. We start off with 0 electrons, and we have to balance the electron number as well. So since we have 0 electrons to begin with, and have 1 electron to end up with, we balance that out with an anti-neutrino. And an anti-neutrino has an electron number of -1. So since we started with no electrons, with an electron number of 0, we have to end up with an electron number of 0. So 0 electrons to begin with, 1 electron and 1 anti-neutrino give us an electron number of 0 to end up with. Now, the mass of a neutrino or an anti-neutrino is negligible for our purposes. They do have a mass, but it's very small relative to all the other particles in the reaction, so we don't have to account for the energy of their mass. Now, a similar reaction would be a proton changing into a neutron plus a positron plus a neutrino. A positron is an anti-electron, and we're going to write that with E+. So this reaction is P for a proton becomes N for a neutron plus E+, that's a positron. And since we started off with no electrons to begin with and wound up with an anti-electron or a positron, which has an electron number of -1, we have to balance that out with a neutrino, which has an electron number of 1. So our nucleon number is 1 on both sides. It's a proton on the left and a neutron on the right. And our electron number is also 0. There are no electrons on the left, and we have a positron with an electron number of -1 and a neutrino with an electron number of +1 to give us an electron number of 0 on both sides of that equation. Now, the mass of a positron is equal to the mass of an electron. Everything else is the opposite. Its charge, for example, whereas the electron has a negative charge, the positron has a positive charge. Whereas the electron has an electron number of 1, the positron has an electron number of -1. And so you can see how these two reactions are related to one another. In one case, we have a neutron turning into a proton, and in the second case, we have a proton turning into a neutron accompanied by either an electron and an anti-neutrino or a positron and a neutrino. Notice that in both of these equations, we've also balanced charge. Charge is another thing that we have to balance. The neutron has 0 charge, the proton has a charge of +1, and the electron has a charge of -1, and the neutrino is neutral. So in the first reaction, we had a neutron with a charge of 0 becoming a proton with a charge of 1, and an electron with a charge of -1, and a neutrino with a charge of 0. So all of those charges added up to 0. So we have 0 charge on both sides. In the second reaction, we have a proton with a charge of 1 becoming a neutron with a charge of 0, a positron with a charge of 1, and a neutrino with a charge of 0. So once again, we have 1 unit of charge on either side of the reaction. And the final reaction that we see, due to the weak nuclear interaction, is a proton plus an electron can combine to change into a neutron plus a neutrino. So a proton plus an electron becomes a neutron plus a neutrino. Let's check our nucleon number. Proton has a nucleon number of 1. An electron is not a nucleon, so it has a nucleon number of 0. And that becomes a neutron with a nucleon number of 1 plus a neutrino with a nucleon number of 0. The electron and the neutrino are not nucleons, so our nucleons balance. Our total charge on the left, we have a proton plus an electron. That gives us a total charge of 0. Neutron and neutrino are both neutral, so they have a charge of 0, so charge balances. And we have 1 electron on the left side, so that gives us an electron number of 1, and that's balanced by a neutrino on the right. A neutrino, which is otherwise referred to as an electron neutrino, has an electron number of 1. So our electron number also balances. So, what are our rules of nuclear reactions? In a nuclear reaction, we must balance the number of nucleons, nucleons being either protons or neutrons. So the number of protons and neutrons have to balance on either side. But a proton can change into a neutron or vice versa. That's allowed as long as we balance the total number of nucleons. We also have to balance the charge. Charge must balance even in nuclear reactions. And also, the number of electrons or neutrinos must balance. An electron and a neutrino count as the same thing for this, and we would give them an electron number of +1, whereas a positron in E+, or an antineutrino would get an electron number of -1. So we have to also balance the electron/neutrino number. And the final thing you do when you're faced with a nuclear reaction is you calculate the energy of both sides to see if you have to add energy to make this reaction take place, or if it will release energy, which means that it may occur spontaneously. Let's talk about nuclear decay. Nuclei decay spontaneously. When doing so results in a net increase in binding energy, or a net decrease in mass as we go from the left-hand side to the right-hand side of the reaction. And the difference in energy goes into the kinetic energy of the radiated particles or photons. The primary decay modes that we see are alpha decay, represented by a Greek letter alpha, beta minus decay. Beta minus decay means the emission of an electron. Beta plus decay, which is the emission of a positron. Related to beta decay is electron capture. Anytime that you can have beta decay, you can have electron capture take place. And the final primary decay mode is spontaneous fission. The decay mode favored by a particular isotope of a particular element depends on the number of protons and the number of neutrons in the nucleus. Take a look at this chart. Here you have a graph where the x-axis is the number of neutrons and the y-axis is the number of protons in a nucleus. So the number of protons tells you the element that you're dealing with. And the number of neutrons tells you which isotope of a particular element that you're dealing with. If you look closely at the graph, you should see something that looks like a green staircase going up from 0, 0 up to the right. That staircase, that green staircase, represents the stable isotopes. Those are the isotopes of a particular element that will not decay spontaneously. And you can see that that's a very small number of isotopes that are stable. All the other known isotopes are represented by pixels of different colors that represent their principal decay mode. Below the stable isotopes in most of the graph, you should see a region that represents beta minus decay. Those are the combinations of neutrons and protons that favor decay by beta minus decay. Beta minus decay turns a neutron into a proton and thus moves you diagonally toward the staircase of stable isotopes. Above the line of stable isotopes, you see a region marked with the color for electron capture or beta plus decay. Electron capture or beta plus decay turns a proton into a neutron, so that would move you down and to the right on this graph, or once again move you diagonally toward the line of stable isotopes. So that's what a nuclear decay does, is it moves you on this chart of isotopes towards the stable isotopes. There is also a region in the upper right-hand corner that is marked with alpha decay being the principal decay mode. And alpha decay removes 2 neutrons and 2 protons from the nucleus. So that moves you down and to the left on this graph. So it moves you once again toward the line of stable isotopes. And finally, there are a few very heavy isotopes up in the upper right-hand corner that decay primarily by spontaneous fission. So each of these reactions moves you on this chart towards the line of stable isotopes. One more thing I'll point out before we leave this chart is notice that in the lower left-hand corner, the staircase of stable isotopes coincides pretty well with the N is equal to Z line, the number of neutrons equal to the number of protons. So for very small atoms, or for very small nuclei, stability happens when you have the same number of neutrons as protons. But as you get more and more protons, the line of stable isotopes deviates from that line where the number of neutrons and the number of protons are the same, such that you need more neutrons than protons. The reason for that is that the electron repulsion between the protons is long range, but the attractive force of the strong nuclear force is short range. So as you get more and more protons in a nucleus, you need even more neutrons to hold the nucleus together, because each proton repels every other proton, but the nucleons only attract their nearest neighbor. So you need more and more neutrons to exert more attractive force than the repulsive force between the protons. First, let's talk about alpha decay. An alpha particle is a helium-4 nucleus, or 2 protons and 2 neutrons. Helium is element 2, so it has 2 protons, and the 4 means that you have 4 nucleons altogether, so that must be 2 protons and 2 neutrons. So as an example of alpha decay, let's consider uranium-238 decaying into thorium-234 plus helium-4, R+, an alpha particle. From a table of isotopes, the atomic mass of uranium-238 is 238.0508 atomic mass units. Now we have to subtract off the mass of 92 electrons. So that would be minus 92 times 0.000549 atomic mass units. And then on the right-hand side of the reaction, we have the atomic mass of thorium, which is 234.0436 atomic mass units, minus 90 electrons, because thorium is element 90, so it would be minus 90 times the mass of an electron, or 0.000549 atomic mass units, plus an alpha particle, or a helium-4 nucleus. The mass of helium-4 is 4.0026 atomic mass units, minus the mass of 2 electrons, so it would be minus 2 times 0.000549 atomic mass units. Now, once again, I got the numbers. I got the mass of these atoms from a table of the isotopes, such as you can find in the back of your book or on many sources on the internet. If we add up all those numbers, and on the left-hand side of the reaction, we have 238.0003 atomic mass units, and on the product side, we have 237.9957 atomic mass units. So we have lost mass, meaning that this reaction will proceed spontaneously. How much energy is released? Well, we'll have to multiply our masses times c squared, which is 931.494 mega electron volts per atomic mass unit. And we get that the energy in the uranium-238 nucleus is 221,695.9 mega electron volts, and the energy in the mass of the products is 221,691.6 mega electron volts. So the energy that's released is 4.3 mega electron volts. Now, most of this energy goes into the kinetic energy of the alpha particle. Momentum is conserved when the nucleus shoots out the alpha particle. Think about a rifle and a bullet. When a rifle shoots a bullet, the momentum that the rifle gives to the bullet is equal and opposite to the momentum that the bullet gives the rifle, so they each get the same momentum, but the kinetic energy of the bullet will be much greater, since the bullet has a small mass and a high speed, and energy is equal to 1/2 mv squared. The energy of the bullet is much, much greater than the energy of the rifle, and that's the same in this case, where the uranium-238 shoots out a alpha particle. The alpha particle is lighter, so it gets most of the energy. Let's work an exercise involving alpha decay. How much energy is released when radium-226 undergoes alpha decay? Now, from a table of the isotopes, the atomic number of radium is 88, which means that the radium has 88 protons and the rest are neutrons. The mass of a radium-226 atom is 226.0254. And you'll also have to know that element 86 is radon, Rn, and the mass of radon-222 is 222.0176 atomic mass units. here's our reaction. 226 radium becomes 222 radon plus helium-4. Now, how did I know this, that this was radon? The atomic number, as I said, of radium is 88. So this is element 88. So it has 88 protons. Helium is element 2. So it has 2 protons. Radon must be element 86. So 88 protons becomes 86 protons plus 2 protons. So from the fact that we started with radium and ejected a helium nucleus, we knew that whatever was left had to have 86 protons, and if you look on the periodic table, that is radon. Now, we also have to conserve the total number of nucleons, so 226 nucleons is 4 nucleons for the helium, for the alpha particle, plus the remainder of 222. So we figured out that this must be radon 222. Now, the mass of radium 226 was given to be 226.0254 atomic mass units, but we have to subtract off the mass. This is the atomic mass, this is the mass of the atom, so you have to subtract off the mass of 88 times the mass of an electron. And I'm just going to leave that like this for the time being, and you'll see why. And that becomes radon, which has an atomic mass of 222.0176 atomic mass units, and we'll have to subtract off the mass of 86 times the mass of an electron, plus the mass of an alpha particle or a helium nucleus, which is 4.0026 atomic mass units for the helium atom, minus the mass of 2 electrons, or twice the mass of an electron. Now notice that here we're subtracting 88 times the mass of an electron. So from this side we're going to subtract 88 times the mass of an electron. Actually, let me carry it on one more step. So this would be 226.0254 atomic mass units minus the mass of 88 electrons. And that becomes, let me add these two numbers together, that would be 226.0176 plus 0026. That would be 0202. 176 plus 26 would be 202 atomic mass units, minus the mass of 88 electrons. So we're subtracting off the same number from both sides. I can add, if I add the same thing to both sides, then I won't affect the difference between the two sides. So I can actually add in, if I add to both sides, plus 88 times the mass of an electron. Then I can cancel this off. Okay, so the difference is the same as the difference between these two numbers. So you can see that we're going from 226.0254 to 226.0202, and we're subtracting 88 times the mass of an electron from both sides, so those electrons aren't going to make a difference when I subtract this mass from this one, or this energy from this one. So if I multiply both of these by c squared, if I multiply these masses by c squared, that would be 226.0254 atomic mass units times 931.494 MeV per atomic mass unit goes into 226.0202 atomic mass units times 931.494 MeV per atomic mass unit. Then our energy on both sides is 226 times 931.494. Let me try that again. 226.0254 times 931.494. That gives me 210,541.3 mega electron volts, where the atomic mass units cancel out, and that becomes 226.0202 times 931.494, and that is 210,536.5 mega electron volts. So you can see that the energy decreases as you go from the radon to from the radium to the radon plus an alpha particle, and that energy goes into the alpha particle. So the difference is 210,541.3 MeV minus 210,536.5 MeV, and that difference is The difference is 210,541.3 minus 210,536.5, and that is 4.8 MeV. So 4.8 MeV of energy was changed from the mass energy of what we started with into the kinetic energy of the alpha particle. Let's work another exercise involving alpha decay. Show that spontaneous alpha decay of oxygen-19 does not occur. From the table of isotopes, the atomic number of oxygen is 8, and the mass of an oxygen-19 atom is 19.0036 atomic mass units. You'll also have to know that element 6 is carbon, or the element with an atomic number of 6 is carbon, and the mass of a carbon-15 atom is 15.0106 atomic mass units. Okay, so the reaction that we're looking at is oxygen-19 becomes something plus helium-4. Well, if we have 19 nucleons to begin with and 4 go into this, and we know whatever we have left is 15. Oxygen is element 8, and helium is element 2. So whatever we have here must be element 6, because 8 plus 2 equals 6, or 8 minus 2 equals 6. And so element 6 is carbon. So if oxygen-19 were to alpha decay, which means to emit a helium-4 nucleus, then the other product would be carbon-15. Okay, now we were told that the mass of an oxygen-8 atom is 19.0036 atomic mass units. Now we would have to subtract off the mass of 8 electrons to get the nuclear mass here. I told you that the mass of carbon-15 is 15.0106, and then to get the nuclear mass we'd have to subtract off the mass of 6 electrons. And then the mass of helium-4 is 4.0026 atomic mass units. And to get the nuclear mass, we would have to subtract off the mass of 2 electrons. And once again, you can see that we're subtracting the same thing from both sides. So when we're comparing one side to the other, we don't need to worry about actually subtracting off the mass of the electrons. Those are going to, I can add the same thing to both sides. 8 times the mass of the electron. Oops, I'm sorry, 6 right here. That'd be 6, and this would be 2. So I'm adding the mass of 8 electrons to this side, and 6 here and 2 here, so that those cancel out for our consideration. So if we just add up these numbers right here, we have 19.0036 atomic mass units becoming 15 plus 4 is 19.01, and then that would be 26 plus 6, so that would be 32. So what you see here is that we have 19.0036 atomic mass units becoming 19.0132 atomic mass units. So there's more mass over here than we had to begin with. So that means in order to make this reaction happen, we would have to give mass to the, we would have to give energy to the oxygen to make up for the mass energy difference. So since this number is greater than this number, this reaction will not occur spontaneously. You have to add energy, or equivalently add mass, to this side in order to get it to go to this side. So this reaction does not happen spontaneously. So alpha decay occurs when a nucleus emits an alpha particle, or 2 protons bound to 2 neutrons, which is also a helium-4 nucleus. And this moves the nucleus towards the line of stability. Beta minus decay occurs when a nucleus emits an electron, or in other words, a neutron emits an electron and changes into a proton, and this also moves the nucleus towards the line of stability. A beta minus particle is an electron. For example, free neutrons undergo beta decay. A neutron becomes a proton plus an electron, that's our beta minus particle, plus an anti-electron neutrino. So just to check, we've balanced our number of nucleons, a neutron on one side and a proton on the other. We've balanced charge. The neutron is neutral, the proton is +1, the electron is -1, the neutrino is 0, so we have 0 charge on both sides. And we balanced our electron number. We have an electron number of 0 on the left and the electron has an electron number of 1, the neutrino has an electron number of -1, and the proton has an electron number of 0. So we have a 0 electron number on both sides. The mass of a neutron is 1.0087 atomic mass units. The mass of a proton is 1.0072 atomic mass units. The mass of an electron is 0.0005 atomic mass units. And the neutrino has negligible mass, or 0.0000. So we have a total of 1.0087 atomic mass units on the left-hand side and 1.0077 on the right-hand side, or we have 939.6 mega electron volts on the left-hand side and 938.7 mega electron volts on the right-hand side. So a neutron will spontaneously decay into a proton plus an electron. So free neutrons are not stable. They will decay, and they decay pretty quickly. They have a half-life, which we'll learn about later, of about 10 minutes. Let's work an example with beta minus decay. How much energy is released when potassium-40 undergoes beta minus decay? From a table of isotopes, the atomic number of potassium is 19, and the mass of a potassium-40 atom is 39.9640 atomic mass units. Identify the daughter nuclide. From a table of isotopes, the element with the atomic number of 18 is argon, and the element with the atomic number of 20 is calcium. I'll give you the atomic mass of the correct answer once you've identified the daughter isotope. So go ahead and get started with that, please. Okay, we have potassium-40, and I'll just make a note that potassium is element 19, or it has 19 protons, and it becomes something plus an electron plus an electron antineutrino. The potassium, what happened inside of the potassium is that a neutron became a proton plus an electron, and the electron was emitted. So the nucleon number has to be the same, so the 40 has to be the same. And since a neutron over here became a proton, this side has to have an atomic number of 20, or 20 protons, and element 20, or the element with 20 protons, is calcium. So potassium-40 decays by beta minus or electron minus decay into calcium-40. The atomic mass of calcium-40 is 39.926 atomic mass units. The atomic mass of potassium-40 is 39.9640 atomic mass units. The atomic mass of an electron is 0.0005 atomic mass units plus 0.0000 over here for the neutrino. Now, for the potassium-40, this is the atomic mass, so we have to subtract off the mass of 19 electrons, so minus 19 times the mass of an electron. And for calcium, which is 20, this is the atomic, this is the mass of the neutral atom, so we have to subtract off the mass of 20 electrons. So minus 20 times the mass of an electron. And notice what we have here. We have minus 19 times the mass of an electron. We have 20 times the mass of an electron plus the mass of an electron. So actually these will cancel out. So this is minus 20, this is minus 19 times the mass of the electron. This is minus 20 plus 1 times the mass of the electron. So these will also cancel out when we're comparing one side to the other. So here we have 39.9640 atomic mass units becoming 39.926 atomic mass units. So we have a difference. If I subtract, so this number goes into a smaller number. So this large amount of mass goes into a smaller amount of mass. So this has more energy than this, so we are releasing energy when we do that. Let me calculate the energy. 39.9640 atomic mass units times c squared, which is 931.494 MeV per atomic mass unit, goes into 39.926 times 931.494 MeV per atomic mass unit. Atomic mass units cancel out, and we are left with 39.964 times 931.494. We have 37,226.2 goes into 39.926 times 931.494 goes into 37, and that would be, MEV, 37,190.8 MEV. So the difference is, that would be 37,226.2 minus 37,190.8. That would release 35.4 MeV of energy. And that is what we were asked to find. So, that is beta minus decay, or when a nucleus decays by having a neutron turn into a proton and radiate an electron. The electron is the beta particle. That's beta minus decay because the electron is a negative particle. There is a very similar reaction, beta plus decay, when a positron is emitted, and we'll talk about that next time. Until then, think physics.